Friends, welcome back in the second part of nuclear magnetic resonance spectroscopy. In the first part, we have seen what is NMR, why it is called as nuclear magnetic resonance spectroscopy. We have seen the historical perspective and which nuclei are said to be NMR active, that is based on the spin quantum number. We have also seen some of the basic theoretical aspects related to the theory or the principle of NMR spectroscopy. So we have seen what is spinning nucleus, what is applied magnetic field, how the nuclei will behave under the influence of applied magnetic field, what is precessional motion, what is gyroscopic motion, and so on. So if you have not watched first part, the description link is given below. You can watch that and then we can proceed for this second part. Now in the second part, we are going to discuss again various aspects. So what is NMR spectra? NMR spectra is a plot of chemical shift on x-axis, and on y-axis usually we have the signal intensity. Now again here I have represented an NMR spectra of simple molecule ethanol. Here we have the methyl protons. This signal is appearing as an intense signal. Then moderately intense is the CH2 protons, and then we have the OH protons. Now by taking the NMR spectra, it gives lot of information about the structure of particular compound, and this makes the NMR spectra as a very powerful tool for elucidation of particular structure, usually the novel structures. What we do in proton NMR as well as C13 NMR, we plot or we record the chemical shift values for a particular set of protons with respect to some reference standard, that is called as internal standard, because it is added along with sample, that is TMS. So this TMS, which is nothing but a tetramethylsilane, this particular protons are chemically equivalent and they appear at value which is very close to 0, and this value is considered as a value, standard value. It is considered as a 0, and with respect to this TMS peak, the other peaks are plotted. Now by looking at the NMR spectra, we get the below information. First is, here we can observe there are 3 signals. So number of signals correspond to the types of protons. Now in ethanol we have 3 types of protons or 3 sets of protons. So this also known as the chemical equivalence. So chemical equivalence is given by the number of signals. So the number of signal correspond to the chemical equivalence or the type or sets of the proton. Second is the position of the signal, that is the delta value, which is on this particular x-axis. Now we can see here the CH3 protons are appearing between 1 to 2, then CH2 protons are in between 3 to 4, and OH is near to 5. So each type of proton, based on what neighbors they have, they will have a characteristic delta value, and this characteristic delta value will reveals the nature of these protons. For example, usually the CH3 protons appear always in between 0 to 2. So if you are observing the signal in between this particular region, we have the idea there is a presence of this kind of CH3 protons here. Similarly, the aromatic protons in benzene ring or any kind of aromatic system, they usually observe in between 6 to 8.5. So if we are observing any protons in between this particular range, which is a characteristic, we have idea about the type of or nature of the proton. Third is a signal intensity, which we usually integrate with the software. So we integrate each peak, which is indicated here with the red line. So if I integrate this particular peak with the integrator, I will get the information about the number of protons present in that particular peak. For example, if I integrate this particular peak, which is a CH3 proton peak, I will get the integration value as 3 or near to 3. So that indicates this particular peak is corresponding to 3 protons, and these 3 protons are in one particular environment. Then additionally we can get lot of information on the splitting pattern. So what is splitting pattern? It follows the rule n+1, which we will be discussing in detail in the spin-spin splitting. So this splitting pattern gives the number of protons in the neighboring carbon atoms, who are the neighbors for a particular set of protons. For example, in this case CH3 has been splitted here in triplet. So there are 3 lines. So these 3 lines, or this particular splitting of this signal, based on the number of protons in the neighboring carbon atom. So here the neighboring carbon atom is C, which has 2 protons. So n is 2 here, so it will be 2 plus 1, so this is going to split in the triplet. Whereas CH2, the neighboring carbon is having 3 protons, so this has splitted into quartet. So we will get information what are the neighbors and how many protons they have. We can elucidate the structure based on that. And we also get a coupling constant, which is abbreviated as a J value, and this J value has a very important role, especially in type of compounds which are quite complex and which are giving the splitting kind of pattern. So it gives information about spatial relationship between the coupled protons. So we will be discussing all these things in detail in the coming slides. Now this is how exactly the NMR spectra look like. Now this is an spectra of toluene. Here we can see this methyl proton will be giving a very intense peak, and that is again near to 2.5, and if you integrate it, it will be giving 3 protons. So one signal for CH3, and we have 5 aromatic protons. They are appearing in between this aromatic region, that is 6 to 8. Now as per the international convention, there are certain guidelines which is to be followed whenever we record the NMR spectra for the uniqueness. So what we do, NMR spectra is always plotted by taking the TMS value on the extreme right side, which is considered as a 0, and with respect to this all other peaks are plotted. NMR scale is in the delta scale on x-axis, and usually the scale is from right to left. So it is usually from 0 to 12 delta ppm, where we can get all types of protons in this particular kind of spectra. Now we have certain set terminologies. For example, those protons which are appearing towards 0 or towards TMS, they are called as they are appearing in the upfield region, and these protons are basically they are shielded protons, and because of the shielding they require lower frequency. So we have seen to shift the protons from ground state to the excited state, we require a quantized energy, that is a delta E, and this energy difference for the protons which are appearing towards this upfield region or the shielded region, they require lower energy to bring them into a resonance. On the other hand, left side, those protons which are appearing towards the left side towards 12, they are called as a downfield region, and these protons are usually de-shielded and they require higher delta E to bring them into a resonance. Okay, so here onwards we will be referring the terminologies like the protons are coming in upfield or protons are shielded. So we have to consider these particular things. Now in this particular spectra, you can see we are expecting 2 signals, because this CH3 and this CH3, they are giving only one signal together. Okay, so this is a one signal corresponding to both the CH3 because they are in same chemical environment, whereas these 4 protons, they are in same environment and they are giving one particular peak here. So we are expecting 2 peaks for this particular molecule. In this structure, for all these 3 CH3 protons, they are again chemically equivalent and they are giving one intense peak corresponding to 9 protons, 9 methyl protons, and 3 aromatic protons are coming in this aromatic region. So by looking at only spectra, we will get information about the types of protons. From integration, we get the information about the number of protons and so on. Now with that, we can also predict the number of signals in these compounds. For example, CH3, CH2, Cl. How many signals we are expecting here? So you can pause the video, you can practice it and just verify your answers. Now in CH3 here, this CH3 is in one environment, their neighbors are different, and this CH2 is in different environment because their neighbors are different. And Cl is not going to give any particular signal because we are observing only the proton NMR. So this CH2 will give one signal and this CH3 will give another signal. So I am expecting two signals for this ethyl chloride. Then you can consider the other example here. CH2, it has a neighboring atom chlorine and CH2, and then next neighbor is CH3. Whereas this CH2 have different neighbors. So this CH2 and this CH2 is in different environment. And this CH3 is also in different environment, which is totally different from this CH2 and this CH2. And chlorine is not going to give any particular peak because we are observing only the nucleus of the proton. So in this particular structure, I am expecting how many signals? 3 signals. What about the third one? Here we have CH proton, and CH proton is a unique, whereas if you see the methyl protons, so this methyl has immediate neighbor CH, then next neighbor Cl and CH2, Cl and CH3, sorry. Then this CH3 also has same kind of neighbors. That's why this CH3 and this CH3, they are in same chemical environment and they are going to give only one signal, and this CH will be giving another signal. So here I am expecting two signals for this particular compound. Okay, so these are the answers. Now this is what is called as a chemical equivalence. Now all protons found in a chemically identical environment within a molecule are said to be chemical equivalent or chemically equivalent. So these chemically equivalent protons appear at same chemical shift or the delta value. Now when we see these structures, in this particular benzene aromatic structure, we are observing 6 protons, and all these 6 protons are having same environment. Okay, so all these 6 protons, rather than giving 6 signals, they will be giving only one signal of high intensity, which is contributing 6 protons. Similarly, in this structure of cyclopentane, we have 10 protons, and all these protons are in same environment. Their neighbors are exactly same as that of the others. So here also cyclopentane, we are expecting only one signal. Similarly, you can see here in acetone or dimethyl ketone, we have 2 CH3s, and both CH3 are in same environment. This CH3 as well as this CH3, their neighbors are same and they will be giving only one signal. Similarly, for this TMS, that is tetramethylsilane, we have 12 protons which are also in same environment. So all these compounds is going to give only one signal in the NMR spectra. In the second type of example, we can see this particular structure. We have OCH3 or methoxy protons, and here we have the CH2 protons. Now this CH2 and this CH2, is it a chemically equivalent? Because they are present in same environment. So these two CH2 protons are in same environment, they are identical, and that's why they will be giving only one signal corresponding to these 4 protons. Similarly, OCH3 and OCH3, their neighbors are same, so they will be giving another signal. So here 2 signals for this compound. Similarly, for this structure, CH3 and CH3, their neighbors are same, they are in identical chemical environment, so they will be giving one signal, and this 2CH and these 2CH will be giving one signal. So one signal for these 2 CH3 and one signal for these 4 aromatic protons. Similarly, we have this particular structure. Now, though it is similar to the acetone, but in this case one methyl has oxygen attached to it. That's why this OCH3 is different from CH3. So here I am expecting two signals in the NMR spectra. Take this example again. So CH3O CH2Cl. So this CH2 has different neighbors and this CH3 has different neighbors. Therefore, here also it will be giving two signals in this particular structure. Now in this particular structure we can see to this particular carbon we have 3 methyl protons. Now this methyl proton has these neighbors, this methyl proton has these neighbors, and this methyl proton has these neighbors. So I can say all these 3 methyl protons are in same chemical environment. So those protons which are in same chemical environment, they will give only one signal. Then this CH2 is not similar to as that of CH3, so this will be giving another signal, and this CH3 is totally different from these CH3s, so this will be giving the third signal. Okay, now look at the other compound CH3OCH2COCH3. So this CH3 has keto group here, whereas this CH3 has the ethyl linkage here. So this CH3 is in different environment than this, so they will be giving two different signals, and this CH2 is totally different. So again here I am expecting three signals for this particular compounds. So this is what is chemically equivalent protons, or this is called as a chemical equivalence, and this chemical equivalence information can be obtained by recording an NMR spectra. Now if you have understood all these things in a proper way, we can solve these examples. So we have an structure of toluene. So you can see here there are 5 aromatic protons and 1 methyl proton. So how many signals we are expecting in this particular structure? We have to find out the chemical equivalence. Okay, so here we are expecting 2 signals because all these aromatic protons are in same environment, whereas this CH3 is in different environment. So I am expecting 2 signals for this. Then in the second structure we have an attachment of CH2 in between CH3 and aromatic protons. So here all these aromatic protons are in same environment. This CH2 is different and this CH3 is different. So it will be similar to this I have shown in the color coding. So I am expecting 3 signals for this particular structure. Then look at the third structure. Here we have CH3 here, and exactly at the para position we have another CH3. So they are chemically equivalent, and these 4 protons are in another chemical equivalence. So I am expecting 2 signals here, one for CH3 and second for 4 aromatic protons. Now look at the other structure here. We have methyl. Okay, then one CH is here at this particular carbon. So this CH is a unique, it is not similar to this because there is no CH3 here. Then one CH2 and one CH2 here. So this CH2 and this CH2, they are in same environment. This CH2 and this CH2, again they are in same environment, and this CH2 is in different environment. So how many signals? Yes, we are expecting here 5 different signals. That is indicating the chemical structure has 5 sets of protons. 5 type of chemical environment is present in this particular structure. What about this? Here we have the CH, and here also we have CH. So they are in same environment. You can see the neighbors. Then this CH2 and this CH2 is in same environment, and this CH2 and this CH2 is in same environment. So we are expecting here 3 signals for this particular structure. Then when we look at the other structure here, CH3 will definitely give one signal. Then this carbon doesn't have any proton because its valency is fulfilled. Then we have a carbon here, that is CH. So this CH is different than any other protons. So this CH2 and this CH is different. So this is giving one signal. This CH2 and this CH2, are they same? We have to see the neighbors. So this CH2, the neighbors are this one, and this CH2, the immediate neighbor is CH3, whereas for this CH2, immediate neighbor is CH. So this CH2 and this CH2 is totally different. Similarly, this CH, this CH2 and this CH2 is also different. So we are expecting here 6 different signals for this particular compound. So that is how the chemical equivalence is, and how many signals we can expect, that totally depends on the kind of environment present in a particular molecule. Now next concept is the chemical shift. Now chemical shift is represented as, or it is expressed in delta units as ppm. Now chemical shift is nothing but a position of signals. Now the difference between the absorption position of protons with respect to our internal standard TMS is referred as a chemical shift. So this is basically a dimensionless number, and it is independent of field strength. So whatever field strength you are taking, whether it is a 400 megahertz or whether it is a 600 megahertz, so this delta value remains same. So I have represented here an simple spectra of benzyl alcohol, where it has how many sets of proton? 5 aromatic protons in a one set, CH2 protons, 2 CH2 protons in a second set, and 1 OH proton in the third set. So we are expecting 3 signals here for this benzyl alcohol, 1, 2 and 3. Okay, and look at the position of these signals. They are characteristic. So I told you aromatic protons usually appear in between 6 to 8.5, and we are observing these signal. So that indicates there is a presence of aromatic ring in the structure. And we have the other protons also. Okay, so at what position these protons are appearing, the signal is appearing, that is a characteristic similar to the IR frequencies for a particular functional group. And we have an internal standard tetramethylsilane. This peak is considered as 0, and with respect to this 0 we are plotting all other peaks. Okay, and we have again the same thing what we have discussed. Towards right side it is upfield, shielded protons, and they require lower frequency. Towards the left side these protons are downfield, they are deshielded, and they require higher frequency. So they are, those which are in the left side, they are appearing at higher delta, and those which are in the right side, they are appearing at lower delta value. Now we can also find out the chemical shift if we have the value of mu. Chemical shift can be calculated easily with this particular formula. Delta, which is a chemical shift, this is equal to nu s. So this nu s is nothing but the frequency of sample in the hertz. So whatever sample we are recording, what is its frequency in hertz, that we have to write it here, minus the nu of TMS. So this nu of TMS is nothing but the frequency of our internal standard TMS, again in the hertz unit. Then we have to divide this with nu 0, that is the operating frequency of the instrument, and that is usually taken in the megahertz. So whatever the operating frequency of the instrument, for example in the earlier spectra the operating frequency of the instrument is 60 megahertz, it is a 60 megahertz. Okay, so we can calculate. For example, the OH signal on the spectrum is at 144 hertz, higher frequency than the TMS. So we can see here, this is a OH signal, and this is requiring 144 hertz frequency to bring them into a resonance. Okay, that is with respect to TMS. How many delta units in ppm does this correspond if instrument is operating at frequency 60 megahertz? So we can consider this 144 is a sample frequency in hertz minus the frequency of TMS in hertz, that is 0. So the value will be 144 divided by operating frequency of the instrument in megahertz, it is 60. So 144 divided by 60, that is coming to 2.4 ppm. So that is a delta value, that is the chemical shift we have calculated with this. So you can see here, this OH proton are requiring 144 hertz energy through this frequency wave to bring them into a resonance. And you can see, if you consider the x-axis or the delta scale, it is very near to 2.5. okay, so that is how we can calculate the delta value. Now so far we are discussing about the internal standard and TMS. So now question is, why this TMS is used as an internal standard? Now this is a structure of TMS where we have a silane at the center which is highly electropositive, and to this silane we have 4 methyl protons. Okay, so because of the 4 methyl proton, it is called as a tetra, and we have a methyl group attached to this, so it is a methyl, and we have at the center it is a silane, so it is a tetramethyl silane. And this is the compound which is very widely used as an internal standard to record an NMR spectra when you are taking proton NMR and carbon 13 NMR or C13 NMR. Okay, so this TMS is very widely used. Now why this TMS is widely used for recording an NMR spectra of proton and carbon 13? So these are the points which are very important and very frequently it has been asked in the examination. So this TMS is used as a internal standard because it is universally accepted as a standard or reference. Then this TMS has 12 magnetically equivalent protons. So we can see this CH3, this CH3, all these protons, they are in the same chemical as well as magnetic environment. So we will be discussing again in further slides what is magnetically equivalent protons, right? So all these 12 protons are not only in chemical environment, identical chemical environment, but they are also in magnetically identical environment. It gives very sharp signal even at the lowest concentration. Okay, so we need not add too much of this internal standard. This internal standard is added to the sample solution at 0.012 to 1% as an internal standard. So very less concentration is required, and at less concentration or at low concentration it is giving a very sharp signal. And more importantly, the TMS is chemically inert, so it is not going to alter your solvent or it is not going to alter your sample. So it is not chemically reacting with anything else, it is inert and therefore it is used. Another advantage of TMS using as an internal standard is its boiling point is very less. Its boiling point is near to 26.5 degrees Celsius. So you can easily evaporate after analyzing your sample, especially the valuable samples. So this NMR technique is non-destructive technique. That is another advantage of NMR spectroscopy. So if your sample is so valuable, you can analyze or record NMR spectra, and once the experiment is done, you can recover back your sample if you require, and the TMS can be easily evaporated because its boiling point is very less. This TMS is soluble in most of the organic solvents. So we require solvents, usually the deuterated solvents if you are recording NMR spectra with proton nucleus, and we need to solubilize our solid samples or we need to dilute our liquid samples. So in such case, this TMS should have the miscibility. So it is miscible with almost all the organic solvents except the water and deuterium oxide. Okay, so TMS is not soluble in water and D2O. In such now additionally, other than C13 and proton, if you are recording NMR spectra of these nuclei, that is fluorine 11, then we have to use internal standard as CFCl3. If you are recording phosphorus 31, you have to use H3PO4. If you are using N15, recording N15 NMR spectra, then liquid ammonia can be used. And if you are recording or observing the nucleus of oxygen 17, then you can use water as a internal standard. Okay, so with this we'll stop here, and we will discuss the remaining in the third part. Thank you.